Hello. Today we have selected a different type of lecture. In fact, I thought that coming to the board and writing a bit of theory covering various topics is fine, is necessary, but at the same time, one very important aspect in mathematics particularly is problem solving skills. And I cannot overemphasize the fact that these kind of skills can only be acquired by practice, practice and practice. So we've learned at a very early age that practice makes a man perfect. Practice makes a man perfect. So unless one is continuously practicing with whatever is the syllabus or course being covered, the chances of errors creeping in, mistakes creeping in, goes up a little higher. So with that in mind, I have designed this lecture to read as assorted problems on the mean value theorem. This is part of the 102B course, mean value theorems, beta gamma functions, maxima and minima of functions of a single variable and so on. Whatever problems I felt are good, I have selected them. So I'll put up the first problem after rubbing out what is there on the board. The first question reads as follows. Show that for any quadratic function of the form px square plus qx plus r. This is a quadratic function. We are not taking a quadratic equation, so we don't write is equal to 0. The problem goes on. Lagrange's theta is always half. Always half. In other words, it is independent of two things. It is independent of what are the values of p, q and r. For example, 3x square plus 2x plus 5 or 2x square minus 3x plus 2. Whatever are the values of p, q and r, it only has to be a quadratic function, and Lagrange's theta, in other words, the theta of Lagrange's mean value theorem is always half. And independent of one more thing, and that is the interval that is chosen for the Lagrange's mean value theorem. So if this question has been noted down mentally or in your workbooks, then it's fine. We will rub out the question and just keep the essential parts on the top. So before rubbing it out, we once again state the problem. Show that for any quadratic function of the form px square plus qx plus r for different values of p, q and r, the Lagrange's theta is always half, independent of p, q, r, independent of the interval that is being considered. So we just start doing the problem. So here we have fx is equal to px square plus qx plus r. This obviously means that f dash x is 2px plus q, but we'll come to that later. Let us choose an interval a, b. AB, general interval, to apply the LMBT to this particular function. So we've taken fx to be px square plus qx plus r, and we have taken a general interval a to b. A and b are perfectly general real numbers, and b is greater than a, as we can see. Now from here, f dash x, which we will need, is nothing but 2px plus q. 2px plus q. So with this and whatever we have done now, we will apply the LMBT to this quadratic function. LMBT states that there will be a C, at least one C, one C in this open interval AB, such that FB minus FA over B minus A is F dashed C. Now here FB is, if Fx is Px square plus Qx plus R, then this implies that we must have Pb square plus Qb plus R, this is Fb, minus Fa, Pa square plus Qa plus R divided by B minus A must be equal to 2Pc plus Q. 2Pc plus Q. This is F dash C. So we will demonstrate that there indeed is a value of C, and we will get to the business of theta a little later. Now, if we rub out this part and simplify the algebra, the numerator is, this implies P into B square minus A square plus Q into B minus A over B minus A is equal to 2P. We know that C can be written as A plus theta H, where H is B minus A. 2P A plus theta H plus a Q. Plus a Q. This is 2P. C is A plus theta H. Theta lies between 0 and 1 plus this Q. Now, we will rub out a little bit of space from the top and carry on working up. We can see that the numerator has a factor of B minus A. We can write this out. In fact, this implies P into B minus A into B plus A plus Q into B minus A over B minus A is 2P A plus theta h plus q. Now, what we can do is we can remove a common factor b minus a, because since b is not equal to a, it's not 0, we can divide by b minus a. So, we remove the common factor b minus a and get from here the implication is p into b plus a plus q is equal to 2p a plus theta into h plus q. Now, this is getting closer to home, because now we can write, after removing this q from both sides, we write and this p there. So, the relation that emerges now is b plus a is equal to 2 into a plus theta b minus a, that is h, and no q. So, this is equal to 2a plus 2 theta into b minus a. If I take this a on this side, we get, the implication is very simple, b minus a is equal to 2 theta into b minus a, and this implies theta is equal to half. So, we are absolutely home. This is what we set out to prove, and we have just proved and completed the first problem. The significant part being that, number one, if the function is quadratic, theta is equal to half has a geometrical significance, which means that if the interval is a to b and h is b minus a, then theta is equal to half is suggestive of the fact that C lies exactly between A and B at the midpoint. So, C is the arithmetic mean of A and B.